In the previous videos, we have introduced CIGS for the production of thin film solar cells. We have discussed the two different deposition approaches and discussed the traditional cell structure. In this video, we will show how cells are most commonly interconnected in solar modules by means of monolithic integration. And secondly, we will discuss the toxicity and the abundance of the elements required for CIGS solar modules. The interconnection between CIGS solar cells is achieved by monolithic integration, as was also discussed previously in the video series on thin film technologies. Usually, separate solar cells in lateral direction are made by scribing the layers, most often by using an absorbing laser. The molybdenum back contact receives the first laser scribe prior to the CIGS deposition step. A second scribe is performed after CIGS deposition, followed by the cadmium sulfide buffer layer and the zinc oxide TCO layer. A third laser scribe divides the material into cells of the right size, while the connection between the front TCO layer of the first cell and the back contact of the second cell is located here. The current can then flow through the interconnection as is shown here. One can clearly see that some of the cell's area is lost by the laser scribes and the interconnection. The aperture area that limits the operational cell is thus somewhat smaller than the total cell area. Now that we have seen the structure of a CIGS solar cell and how a module can be produced with monolithic integration, we will briefly discuss the cadmium sulfide buffer layer. There is some debate about using the element cadmium in the solar cell because of its toxicity. Nevertheless, it is used in the traditional cell stack in the form of cadmium sulfide. This material is placed in between the N-type CIGS layer and the front TCO layer to provide lattice matching and hereby reduce the defect concentration. This is also the reason why the cadmium sulfide layer is referred to as a buffer layer. Furthermore, the N-type cadmium sulfide layer helps to form a better buried junction in the P-type CIGS. An advantage of using this material as buffer layer is that it can be produced fairly cheap, at a low temperature and on a large area using chemical bath deposition or CBD. Here we see an illustration of a lab-scale chemical bath deposition setup. The substrate is submerged in a precursor fluid containing cadmium and sulfur, and a thin layer of cadmium sulfide will then deposit on the substrate from the solution. The growth rate depends on the solution temperature, composition, the deposition duration, and the topographical and chemical nature of the substrate. Although the cadmium sulfide layer has many advantages, the environmental issues made the industry to look for alternatives. This overview shows on the left-hand side the traditional cell structure, along with many alternative structures. Some of the cadmium-free cells can even have a higher conversion efficiency than the traditional cell with the cadmium sulfide buffer layer. However, cadmium is not the only element that causes upscaling troubles for the CIGS technology. We can see from this graph that indium is a relatively rare element in the Earth's crust, and this element is already being used extensively in the display industry, so it has been foreseen that this element may limit the upscaling of the CIGS industry. For this reason, research has been carried out on the so-called casterite semiconductors instead of the chalcogenides such as CIGS. Examples of casterite semiconductor compounds are copper, zinc, tin sulfide, copper, zinc, till selenide, or a combination. The highest conversion efficiency of a cell based on this non-toxic and abundant semiconductor material is 11% on lab scale as presented by the IBM group in 2012. To summarize this video, we have discussed that thin film CIGS solar cells can be interconnected by monolithic integration. The N-type cadmium sulfide buffer layer is placed in between the front TCO and the absorber layer to provide lattice matching as well as to create a heterojunction with the P-type CIGS layer. Finally, we have discussed that the elements cadmium and indium may limit further progress either by the perceived toxicity of the cadmium or by the relatively low abundance of indium. Many alternative materials are available, such as cadmium-free alternative, CIGS solar cells and castorides, which are also indium-free.